This is your presenter, Asloob Mudassar, and I am presenting slide number 18D of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: electronic states of diatomic molecules, energy-wise distribution of electronic states and symmetry properties, electronic spin angular momentum, orbital angular momenta, fine structure splitting, etc. These topics will be discussed in the today's lecture. And you know that this is the fourth lecture of the series on molecular physics. So this lecture is in continuation of the previous three lectures, and also there will also be some more lectures following this lecture. Electronic states of diatomic molecules. We have discussed the electronic ground states of the hydrogen singly ionized molecule and hydrogen molecule, and obtained potential energy curves E of R under different approximate methods. And you know that two approximate methods were discussed: molecular orbital approximate method and the Hitler and London approximate methods. These methods have been discussed in the previous lectures. Now we consider larger diatomic molecules with nuclear charge Za times E and Zb times E, and the number of electrons will of course will be equal to capital N, which is equal to Za plus Zb. So here we are considering that the diatomic molecule is composed of two parts of the molecule. One part is Za times E and the other part is Zb times E. And of course, the total number of electrons present in the molecule will be equal to capital N, equal to Za plus Zb. The molecular wave function will be given by the molecular wave function phi as a function of R1, R2, and so on up to Rn, comma capital R is equal to the summation over Cn and phi n, where phi n are the basis vectors, the basis functions or the atomic functions, and Cn is actually the constants in the linear combination of these expansions. Capital R is actually the separation between two nuclei, that is the nucleus A and the nucleus B, and R1, R2, and so on up to Rn are actually the distances of these electrons from their center of mass. So the molecular wave function phi is always written as a linear combination of many basis functions phi n. Some phi n are atomic orbitals, coordinates centered at nucleus A or nucleus B. Some phi n are the Gaussian functions or Slater orbitals. Physical intuitions are used to optimize phi, as few basis functions are possible, or computational reasoning may be used to minimize computational expenditure. So you see that here when we are solving this problem, that is we are going to find out the value of phi in the expansion of different atomic orbitals or different Gaussian functions or different Slater orbitals. We want to use minimum of these phi n functions so that the computational expenditure can be minimized at the same time. Rigid molecule model is assumed in all these computations. So by rigid molecule, we mean that the capital R, that is the distance between the two nuclei, is fixed. Potential energies Ek as a function of R. So Ek belongs to the electronic state. So potential energies Ek of R for different electronic states are obtained. Such curve has a minimum value Ek evaluated at the equilibrium distance Re. Re is the equilibrium distance, and this equilibrium distance will vary for a different electronic states. So Rek, K stands for the electronic state, and E of K and Ek of R is actually the potential energy corresponding to the electronic state K as a function of capital R, and Ek of R of Ek is actually the binding energy corresponding to the electronic state K evaluated at the equilibrium distance Re of the kth electronic state. So you see that here we are talking about different electronic states Ek, and we shall also be talking about the potential energies in corresponding to different electronic state, and also the binding energies corresponding to the different electronic states. Different electronic states are assigned using the criterion. So you see that due to the following reason, different electronic states are possible. For example, in the order of energies. So if there are different values of energies corresponding to different electronic states, then of course the electronic states will be channelized into the orders of energies. So if the energy is lowest, the electronic state will be lowest in energy, and there will also be some other electronic states with the higher energies. So the electronic states will be categorized in terms of the different energies belonging to the binding energies corresponding to each electronic state. And the second condition is the bisymmetry properties of their molecular wave function. By the symmetry property of their molecular wave function. So you see that molecular wave function may have different symmetry properties, and on the basis of these symmetry properties, the molecular wave functions are categorized and consequent, and of course the electronic state will also be categorized according to that. The third condition is by the angular momentum of the atomic states forming the molecular state, and by the projection of these angular momenta onto the internuclear axis. So you see that in a molecule there will be different electrons, and each electron will have different angular momentum, and we shall say that the angular momentum corresponding to different atomic states. So these atomic states may act as individual quantities, or these orbital angular momenta of different atomic states can also be combined to form the total angular momentum. So on the basis of that one, there will be projections either of the individual orbital angular momenta of different electrons on the internuclear axis or the z axis, or there will be a projection of the total angular momentum capital L of the different of the summation of the different orbital angular momenta of different electrons. So there will be also a projection of the total angular momentum on the internuclear axis or the z axis. So on the basis of that one, the electronic states may have different energies, and they of course will also be categorized according to the value of the total angular momentum of the molecule. The third condition is that by the vector sum of their electron spins. So each electron will have its own spin. The total spin can be found by the vector sum of the spin angular momentum of the individual electrons, and vector sum of these spin electrons will be calculated. So on the basis of these total spin of the electrons, of course the total value of the total spin capital S will be different. So if it differs, it will be different for different electronic states, because of course the electronic states will also depend upon the value of the sum of the total electron spins, and of course their projections on the nuclear separation or the z axis. The last one is by the atomic states into which they dissociate for R goes to infinity. So you see that when you set the condition that R goes to infinity, it means that the separation of the two nuclei, which we are now considered heavy nuclei, so their separation will increase, and they will act as individual atoms with individual atomic states. So the individual atomic states will also infer the individual electronic states of the molecule. And so different electronic molecule states may result depending upon the individual contribution of the atomic states of the molecule under the condition that R goes to infinity. One criterion, many molecular states could be possible. So you see that under all these criteria that I have discussed, corresponding to each individual criteria, many of the molecular states could be possible. For the same value of a projection of orbital angular momentum, many different electronic states having different energies or different spins are possible. So you see that here, since I am talking about that even if there is one criterion, many molecular states are possible. And here I am mentioning that for the same value of the projection of orbital angular momentum, many different electronic states having different energies or different spins are possible. So you see that under one condition, under one criterion, many electronic states could be possible. Electronic states and energy-wise order. So here I am going to discuss electronic states and how the energy-wise order can help us to distribute the electronic states. Let EI of R represents the electronic state of a diatomic molecule where I stands for various quantum numbers. For example, principal quantum number, angular momentum quantum number, spin quantum number, etc. Principal quantum number N, which we usually talk about in atomic physics, this principal quantum number N determines the order of electronic states in atomic physics or in atoms or in individual atoms. So you see that in an individual atom, if we have a higher value of principal quantum number N, it means that we are talking about an electronic state with a higher energy. But you know that in case of molecules, we do not concern about the principal quantum number N, or the principal quantum number is will not appear when we talk about the molecular states. So the N which we talk about in atomic physics, this is generally not true for a molecule, except it is exception is for the Rydberg states that dissociate into a ground state atom A and a Rydberg state atom B, where the higher electronic states corresponds to higher N value. Now you see that if you have a molecule and if you are keep on exciting a molecule, then of course a Rydberg molecule will reach a Rydberg state, that is higher state. And if we are talking about a diatomic molecule, one of the molecule will be in the ground state, whereas the other molecule will be excited to the Rydberg states. Under that condition, we can talk about the value of a principal quantum number N while talking about the Rydberg states. But you know that if we are talking about a heavier atom, as the case is which we are talking about in the today's lecture, we don't, and if we are not concerned with the Rydberg states, there is no need to talk about the principal quantum number N, because there will be no relevance of this principal quantum number with the molecule. The relevance will only appear for the case of a molecular structure when we talk about the Rydberg states. For lower states, that is the states which are non-Rydberg states, energy levels are characterized by angular momentum quantum numbers only. That is the orbital angular momentum quantum number and the spin angular momentum quantum number. These two quantum numbers will then determine the energy state of the molecule. It is thus no longer meaningful to use principal quantum number for characterization of electronic states in a molecule. Historically, capital X is used to represent the molecular electronic ground state and higher states through photon absorption by capital A, capital B, capital C, and so on, etc. So you see that historically the ground state will be represented by capital X, and the higher molecular states will be through, of course, photon absorption will be referred to as capital A, capital B, and so on. If the ground state is a singlet state in a molecule, then by absorption of photons will lead to excited singlet states. That is, if the ground state is a singlet, the excited states with the absorption of photons will also be singlet states. The triplet states named by small Latin letters A, B, C. These are the nomenclatures for the triplet states represented by small letters A, B, C, etc. and so on, arranged in the order of increasing energy. That is, the lowest triplet state will be designated by small a, and the higher ones will be by small b, small c, and so on. After discovery of new electronic states, the labels A prime, B prime, and so on were also used. So you see that these are the things we can use capital X as the ground state symbol, capital A and capital B as the excited state symbols through absorption spectroscopy. Historically, these two nomenclatures can be used historically. And the other states could be, for example, if the triplet state can be designated by small a, small b, and small c, and so on. But you know that there will be, after the discovery of new electronic states, the labels as A prime, B prime, and so on, these labels can also be used for the excited electronic states. Now you see that I am talking about this electronic states for the case of Rydberg states of a molecule. So let me read the caption first. Two potential curves of Rydberg states in a diatomic molecule. And you know that one of the molecules should be in the ground state, whereas the other molecule will be in the excited Rydberg state. For example, the excited Rydberg states will be the state represented by A star of n plus 1 plus B. So you see that I am considering here in this figure two consecutive Rydberg states. One Rydberg state is represented by the principal quantum number n. The other Rydberg state will be the next Rydberg state will be represented by n plus 1. And you know that I have put a star on A in both of these states. That is A star of n and A star of n plus 1. This A star means that it is an excited atomic, that it is an excited state A of the molecule. And you know that there is no star with B. So B is in the ground state. So the nuclei B is in the ground state. Or you can say that the atom corresponding to B nuclei is in the ground state, whereas the atom corresponding to the A nuclei is in the excited Rydberg state. And I have shown only these two states over here, A star of n and A star of n plus 1. The energy of the red state, which is the potential energy of this red state function, is represented by En of R, and the potential of the curve represented by the black curve is represented by E of n plus 1 of R. And you know that the binding energies has been represented for the two functions. For example, REN is actually the equilibrium separation for the red curve in the state n, and Re of n plus 1 is the equilibrium separation between the two nuclei when they are in the state of n plus 1. So these are the separations between the nuclei at state n and at state n plus 1 of their Rydberg states. And the binding energy in the Rydberg, in the nth Rydberg state is En as a function of En of Ren, where I have defined Ren earlier. And similarly, the binding energy when the molecule is in the state of n plus 1 is represented by E of n plus 1 at an equilibrium separation of Re at n plus 1. So you see that these are the two consecutive Rydberg states of a diatomic molecule in which the molecule A is in the excited state and the molecule in which the atom A is in the excited state and the atom B is in the ground state. And I have shown other relevant quantities also, which are self-explanatory. Now let's talk about the symmetry properties of electronic states. Consider a plane through two nuclei, and let me first of all show you the figure so that you can have an idea. So you see that this is the plane in sky blue. This plane is passing through the two nuclei A and B, and this plane is also passing through the z-axis. The electron is on the top side of this plane, and there is an electron E prime due to the reflection of the top electron through this plane, and the reflected electron has been represented by E prime. Their separation, their distance from the nucleus A when the electron is at the top of the reflection plane is represented by R, and when it is at the reflected electron will be at a distance R prime from the nucleus A. So this sigma is actually the reflection operator. So this sigma will act on psi of r, where psi of r is the wave function of this molecule. So when sigma will act upon psi of r, it will produce psi of r prime. That is, this psi of r prime is actually the wave function under reflection, whereas psi of r is the original wave function and sigma is the reflection operator. So sigma will operate on psi of r and it will produce a reflected wave function psi of r prime. So you see that now I am talking about that plane. So consider a plane through the two nuclei and let us define the reflection of the molecular electron cloud through this plane by the reflection operator sigma. A double reflection brings the molecule back into its original states. We obtain the wave function phi. The following relationship is demonstrated over here. So you see that here I am using two reflection operators using two sigma on the original wave function phi of the molecule. So this can be written as sigma square operating on phi. And since sigma square operating on phi, we will bring the phi back to its original position. So on the right hand side over here, I have written the original phi over here. So you see that it means that when individual sigma will act on phi, it will produce two conditions, either plus phi or minus phi. And you know that the second application of sigma on this plus minus phi will return the phi function back to its original function phi. So here I am talking about only single operation, single reflection operation on the wave function psi on the wave function phi by the operator sigma, which is the reflection operator. And I am producing plus minus phi over here. So you see that I can now define two symmetry functions. Positive symmetry is defined by sigma operating on phi plus will give you plus phi plus. So phi plus, you see that is the same phi as I have discussed earlier, but the only difference is that when sigma will operate on phi, it will produce a positive sign. That is no change in the value of phi after reflection. Such a wave function is referred to has a positive symmetry. Now let's consider another negative symmetry is defined as sigma operating on a wave function designated as a phi minus. It will produce a negative sign over here. So you see that if a wave function can be separated with a negative sign after being operated by sigma, or the reflection of the wave function is viewed in the plane, and if there is a negative sign, if that wave function can be written as a negative multiplication of a negative sign, then of course this will be referred to as the negative symmetry. So you see that here I have a function. We defined the wave functions with the positive, having a positive symmetry and having a negative symmetry, respectively, with a positive sign on the right hand side after reflection and with a negative sign after reflection, respectively. If a wave function is symmetric, corresponding molecular state will be symmetric. That is, if the wave function is symmetric, the molecular state will also be symmetric. So reflection and inversion are shown on the next page. And you know that as far as reflection is concerned, I have shown this diagram and I have explained the reflection phenomena using the operator sigma. Now there is another function that I am going to define next, and that the symmetry of a molecule is defined by the symmetry of the two atomic states forming the molecule. So one symmetry state is due to reflection. So reflection and inversion are shown on the next page. So reflection is what I have discussed, and now I am going to discuss inversion. What is the meaning of inversion and what happens to the wave function under the inversion process? And these two, that is the symmetry of a molecular state, is defined by the symmetry of the two atomic states forming a molecule. So you see that the symmetry of a molecular state will be determined by the symmetry of the two atomic states that will form the molecule. So you see that next I am going to discuss the inversion, because I have discussed already the reflection process in which I have seen how the electronic charge will be seen after reflection, and now I am going to discuss the inversion, that how the molecular wave function will change under the inversion process. And you see that this figure, that is the part B of this figure, is actually going to explain the inversion process. You see that I have x, y, z coordinate axis, and I have two atoms with the nuclei A and nuclei B. You can set the nuclei A at the position of B or the nuclei B at the position of A. That will not change. So you see that I have x axis, the y axis, and z axis, and over two nuclei are located on the z axis. And you see that I have considered only a single electron. In principle, we consider charge of electrons under reflection and also under inversion. But I am not going to discuss the whole charge of whole electronic charge or the whole electronic charge distribution. I am only going to consider a single electron, because the explanation of a single electron under the inversion process will explain that how the rest of the electronic charge distribution will change under inversion. So now consider a single electron shown in red and is connected through a dotted red line at the origin. So under the inversion of coordinate system, this electron will be mapped as E prime. And you know that the arrow from the origin is also shown pointing out towards E prime. So let's see mathematically what will happen. So this I, which is the inversion operator, will operate on the wave function psi of r. You know that before that I have on the wave function psi of r, and it will produce a psi of minus r. This minus r can be represented as r prime. So this psi of minus r can be represented as a psi of r prime. So inversion operator will operate on psi of r. So psi of r is actually the original wave function of the molecule. So when it is operated by the inversion operator I, it will produce a psi of minus r, because in the inversion x will be replaced by minus x, y will be replaced by minus y, z will be replaced by minus z. It means r will be replaced by minus r. So this r minus r will be represented by r prime. So this is the inversion operator. So let me read the caption at the end. So the top diagram, reflection of all electron coordinates at a plane through the two nuclei, and B, inversion of all electron coordinates at the origin. So you see that in the previous pages, I have explained the reflection process in the text. Now I am going to discuss the inversion process using some text paragraphs. For homonuclear diatomic molecules, with Z is equal to ZB, the inversion of all coordinates at the origin is another symmetry operation which defines the parity of the molecule. So you see that this inversion process is actually connected with the parity of the molecular states. So you see that I square will operate on phi of r. That is, I am operating the original wave function. Either you call it psi wave function or phi wave function. In the diagrams, I have used it as a psi wave function, whereas in the text, I have used phi wave functions. Both are equivalent because they explain the same things. So you see that this is the original wave function of the molecule, which is being operated twice by the inversion operator I. And you know that when you will operate the wave function twice by the inversion operator, it will trace back the wave function to its original form. So on the right hand side, I have the original wave function phi of r. So it means that a single application of the inversion operator on phi of r will produce two conditions, either plus minus phi of r, either plus phi of r or minus phi of r, because the second application of I as given in equation number 92 will follow the equation as given in equation number 92, whether I am using plus sign with the phi of r or negative sign with the phi of r as shown in equation number 93. So it means that there are two options with plus sign and with minus sign. And you know that by definition, when this inversion operator will operate on the wave function phi, it will produce phi of minus r. This is the basic definition of inversion. And I have used this definition by another application of the inversion operator I on both sides, and I have produced the result depicted in equation number 92. So the basic definition is this of the inversion operator. When inversion operator will operate on the wave function phi of r, it will produce phi of minus r. So if phi of minus r is equal to phi of r, then I shall talk about the even parity. If phi of minus r is equal to minus times phi of r, then I shall talk about the odd parity. So the molecule can have even parity as well as odd parity. So from the last two equations, I can write phi of r is equal to is equal to plus minus phi of minus r. So if phi of r is equal to plus phi of minus r, then the wave function has even parity. If phi of r is equal to minus times of phi of minus r, then the wave function has odd parity. German words gerade, which stands for even, and ungerade, which stands for odd, are used. So we can use with grade, I can use a small g, and for ungerade, I can use small u. So I operating on the wave function, which is a grade wave function, which is an even wave function. I shall produce phi g of minus r, and since this is a grade wave function, it will produce having even property. It will produce phi of g of r. And now I am operating the inversion operator on phi of u. And you know that phi of u means that it is an odd function. So when phi will operate on phi of u, it will produce phi of u of minus r, which will be equal to minus phi u of r. This parity property is only present for diatomics with equal nuclear charges. So you see that here I have discussed these parity properties of the molecule under the condition that the diatomic molecule are the homonuclear. That is, the two atoms in forming the diatomic molecules are the same molecule, are the same atoms. So you see that here I have discussed in this section two properties. One is the inversion property, and the other was the reflection property. And on the basis of that one, I have said that it could have these conditions. That is, it can have a positive reflection with a positive sign. The reflection will be referred to as a positive. It may have a negative reflection, and we can use negative sign. So the symmetry property of the molecule could be positive. Positive mean this condition, and when I am talking about that the molecule has a negative symmetry, it means that I am talking about this condition. The next is I am going to discuss electronic angular momenta. You know that electron will have two angular momenta. One is the orbital angular momenta, and the other will be the spin angular momenta. So both these angular momenta and their projection on the z-axis, which is the internuclear axis of the two nuclei, will also be discussed. That is the projection of these angular momenta on the internuclear separation will also be discussed in the current section. So electronic angular momentum is the title. Each electron in a molecule has orbital angular momentum Li. So Li stands for the orbital angular momentum of the ith electron. And spin Si is the spin angular momentum of the ith electron. As the potential in which the electron moves is non-symmetrical, as the potential in which the electron moves is non-symmetrical. Of course, you know that we have discussed that our molecules have a potential which is non-symmetrical. From the very beginning, I have been discussing that the molecules face non-symmetrical potential. That's why we use the cylindrical coordinate system to explain the parameters of the molecules. So as the potential in which the electron moves is non-symmetrical, the orbital angular momentum is not constant in time and precesses around the symmetry axis of the non-rotating molecule. And this symmetry axis, you know, that is the z-axis in the cylindrical coordinate system. For states with the wave functions of cylindrical symmetry, this is the space fixed internuclear separation, internuclear axis or the z-axis. So you see that in this case we have the z-axis or the cylindrical axis which is fixed. The projection on this axis is this. So you see that here I have written an equation Lz is equal to lambda times h bar, where Lz is the z projection of the angular momentum on the z-axis. So Lz is equal to lambda times h bar. So lambda is actually the projection, and I have multiplied it with h bar so that I can have the units of the angular momentum. So the z component of the angular momentum, orbital angular momentum of the electron, which is Lz, is equal to lambda times h bar, where lambda is the projection of the vectorial form of the angular momentum on the z-axis, where lambda can be written as the magnitude of ml, where ml, you know that in the atomic physics we have used the term ml, where ml is the orbital magnetic quantum number of the electron. So here in case of a molecule, we consider lambda, which is the absolute value of ml. This has been explained in one of the lectures in the previous lectures. So lambda is the projection quantum number. So you see that in case of atomic physics, we normally talk about Lz. And in case of molecular physics, we talk about the projection of Lz on the z-axis or the internuclear axis. That is the axis between the two nuclei. And we talk about the projection quantum number L lambda, and we don't talk about Lz much in molecular physics. So in molecular physics, we shall be talking about the lambda, which is the projection quantum number. The precessing electron produces a magnetic field in the z direction. So you see that when electron is revolving around the z-axis, it will carry a precessional motion with its angular momentum L about the z-axis. And that angular momentum of the z-axis will produce a magnetic field along the z direction. For small atoms, which means small z, interaction between mu L and mu S, that is the orbital magnetic moment and the spin magnetic moment. The interaction between these two, which also referred to as the LS coupling, is weaker. For smaller molecules, LS coupling is weaker than the coupling of the spin angular momentum and the magnetic field of the molecule. So for small atoms, S will couple with the magnetic field. Li and Si will precess independently around the internuclear axis. Because they are not coupling together, they will be behaving as individual quantities. So Li, that is the orbital angular momentum, and the spin angular momentum of the individual electrons will carry out their individual precessional motion about the internuclear axis. The S, that is the spin angular momentum projection, the projection of which is Sz is equal to sigma h bar. For the orbital projection, we used lambda, and for the spin projection, we used sigma, small sigma. And to give it a unit of angular momentum, I have multiplied it with h bar. So Sz is equal to, that is the z component of the spin angular momentum, that is which is the projection of the vectorial form of S on the z axis. So Sz is equal to sigma times h bar, where sigma is the spin projection quantum number. So you see that in the molecular physics, we shall now be talking about more of lambda, which is the orbital projection quantum number, and we shall also be talking about small sigma, which will be the spin projection quantum numbers. The molecular electronic state is then characterized by the quantum numbers lambda, sigma, and S. So you see that these three quantum numbers will be frequently used in order to characterize a quantum state of the molecule. Lambda is of course the projection of the orbital quantum number on the z-axis. Sigma is the projection of the spin angular momentum on the z-axis, and S you know as the spin quantum number. The sum of the two projections, omega h, will be equal to lambda times h bar plus sigma times h bar. So sum of these two quantities will give you another total projection quantum number omega. This omega will also be explained with some figures in the next slide. So for molecules with more than one electron, the coupling order of different angular momenta depends on the strength of different interactions. So you see that when we have a molecule with more than one number of electrons, then of course the process of interactions could be different depending upon the strength of these angular momenta. So different schemes can then be realized in order to determine the state of the electron, state of the molecule. For example, Li and Li interaction, that is the orbital angular momentum of one electron will interact with the angular momentum of the second electron. You may more precisely write as Li dash Lj. So this is the interaction between the two orbital angular momenta. So if this interaction is stronger than the Li and Si interaction, and you know that this is the interaction of the orbital angular momentum with the spin angular momentum. So if Li interaction is stronger, the total orbital angular momentum is written as capital L. So capital L is actually the summation, vectorial sum of individual orbital angular momentum of the individual electrons. And the spin will then be written as total spin will be equal to the sum of the vectorial spins of the individual electron, as given by equation number 99 and equation number 100 respectively. Now you see that I am going to explain this equation. Although this is very simple, that is the omega h bar, we are actually writing it as a sum of two quantities lambda h bar and sigma h bar. But actually it is also have physical intuitions, because the angular momentum of the both electrons is actually carrying out a precessional motion, not about sometimes about z-axis, but not necessarily about z-axis, but around a line which is parallel to the z-axis. This is more accurate statement. But you know that here I have shown the projections of L, orbital angular momentum L, and the spin angular momentum S of a single electron on the z-axis. So you see that this is what I am considering a single electron over here in a molecule. The projection L will produce a projection quantum number lambda, and the Lz component will be, that is the Z component of L will be represented by lambda h bar. And I have the spin angular momentum S. The Z component of the spin angular momentum, which will be represented by Sz, is equal to sigma times h bar. So you see that these two projections will add up by head to tail rules according to the figure shown over here. Because L and S are not coupling. So if we want to add a total angular momentum, that is L and S, if we want to add them, then of course they will be added by head to tail rule. That is, their projection will be added by head to tail rules. So the projection of SZ, LZ and LZ will be combined together, which is shown as omega h bar is equal to lambda plus sigma times h bar. Separate precession of angular momentum L and the electron spin angular momentum S around the z-axis for weak spin orbit coupling is shown. And you know that when we are talking about the weak spin orbit coupling, it means that L and S are not coupling together to give you the resultant orbital, to give you the resultant magnetic angular momentum, but they have their projections on the z-axis respectively by LZ and SZ, and their projections will combine vectorially. So we have omega z is equal to sigma plus lambda times h bar. Now you see that here I am considering that the individual Li are going to couple to form a total angular momentum capital S, and the individual electron having angular momentum, spin angular momentum Si of individual electrons will add up together to give you the total spin capital S of the system. So capital L is the total angular momentum of the molecule, and capital S is the total angular momentum of the total spin angular momentum of the electron. The projection of capital L on the z-axis will be represented by capital lambda. And if you want to calculate the z component of this capital L, then the z component of capital L will be equal to lambda times h bar. You have to multiply with the h bar to get the units of angular momentum. So similarly, you have capital S and its projection is represented by sigma. Its projection on the z-axis is represented by sigma. And if you want to write the z component of a capital S, then the z component of a capital S will be equal to this sigma times h bar. So you see that I have used, in the previous figure, you know that I have used small lambda as the projection of L and small sigma as the projection of S. Now since I have capital S due to many electrons, capital S due to many electrons, So I have used the symbol as capital lambda and capital sigma. So when they will combine, I have used capital omega, and in the previous diagram I have used small omega. So when I have many electron system, I shall be using capital quantities as the projection of capital L on the z-axis is capital lambda, and the projection of capital S on the z-axis is capital sigma. And if you add them together, as I have added previously, small lambda and small sigma, similarly you can obtain capital omega is equal to capital lambda plus capital sigma. So this is written for a molecule having many electrons. So let me explain the caption of this figure. Separate precession of angular momentum L, capital L, and the angular and the spin angular momentum capital S around the internuclear Z axis for weak spin orbit coupling. That is L and capital S are behaving independently in a weak spin orbit coupling. Now you see that in this diagram, I am assuming that the spin orbit coupling is not weak but stronger. So this is the case of strong spin orbit coupling, in which capital S will add with capital L will add victorially with capital S to form total angular momentum J of the molecule, and capital J precesses about the z-axis with Jz is equal to sigma times h bar. So this is capital J carrying out a precessional motion about the z-axis, which I have shown in with a blue loop. This blue loop is centered at the z-axis, and the vector J, also shown in the blue, and its vectorial vector is also shown in the blue, is carrying out a precessional motion about the z-axis, and this is the case of strong coupling between a strong spin orbit coupling. And if you want to find out the z component of this capital J, it will be given by Jz, which is actually the projection of omega times h bar. And you know that I have also shown the projection as omega in the previous diagram. Capital omega is the projection, is the resultant projection. And similarly, I am going to give you the capital omega times h bar, which is actually the projection of the angular momentum J on the z-axis, referred to as Jz. So Jz is the Z component of the total angular momentum of the molecule on the Z axis, and it has a value equal to omega times h bar. And I am going to explain next the summation of these quantities. So capital S and capital L and capital S precess independently around the internuclear axis, forming the constant projection. So Lz is equal to capital lambda times h bar, and Sz is equal to sigma times capital sigma times h bar. So these will have fixed values, that is capital lambda is fixed, capital sigma is fixed. Electronic states with capital lambda is equal to 0 will be referred to as the sigma states. You know that don't confuse this sigma with the sigma I have used in equation number 102. So electronic states with capital lambda is equal to 0 are called sigma states, and with the capital lambda is equal to 0, the molecular state will be called pi states, and when capital lambda is equal to 2, the molecular states will be referred to as the delta states. And similarly, when capital lambda is equal to 3, the molecular states will be referred to as the phi state. So you see that these are the molecular states. Sigma states corresponding to lambda is equal to 0, pi state corresponding to lambda is equal to 1, delta state corresponding to lambda is equal to 2. These are the three initial states that I have discussed for a molecule. So you see that when you are going to write down the molecular states, like the one you write the electronic states for atoms. Similarly, you can write down the molecular states for the molecules. Then you will be using the symbols as sigma, pi, delta, or capital phi. These will be the symbols that will be used to represent a molecular state. Note the projection of magnitude of ms is also designated by the Greek letter sigma. And you know that this Greek letter sigma is what I have shown the projection also. For example, this is the projection of the spin represented by the capital sigma. So don't confuse this projection with the projection with the states of the molecule. Molecular states would be sigma. This sigma is not the projection, but this is the molecular state corresponding to capital lambda is equal to 0. Similarly, with capital lambda is equal to 1 and capital lambda is equal to 2. The project, okay, this is what I have explained. So for large spin orbit coupling, angular momentum L and orbital angular momentum L, spin angular momentum S of each electron couples independently to form G. This is a small g. And the total angular momentum becomes capital J is equal to summation over all individual Ji. So Ji is actually the resultant angular momentum of the individual electron. So if there are, so this is the ith electron, Ji in the vectorial form is actually the total angular momentum of the ith electron, having orbital angular momentum Li and spin angular momentum Si of the ith electron. And you can combine them, that is sigma, that is summation, vectorial sum of all Ji will give you the total J of the molecule. Capital J precesses around the internuclear axis with the projection Jz is equal to capital omega times h bar. I have explained all these quantities in the figures above. The quantum number omega, which is the total projection, is well defined, and the quantum numbers lambda, sigma, capital sigma are undefined. So you see that for the case of molecular physics, the quantum number capital sigma is well defined for many electron system. This capital sigma is well defined, and the quantum numbers which we usually use for individual electrons, lambda, sigma, and for more electrons, capital lambda, capital sigma are not defined, are undefined. So only one parameter, that is capital omega is well defined. A molecular state for R goes to infinity, under which the molecular state dissociates into two atomic states which have orbital angular momentum La and Lb with the projections MLA and MLB on the internuclear axis. The resultant projection lambda, capital lambda of the molecular state can then be written as. So you see that this is what we are writing under the condition that the two molecules dissociates in a molecule with R goes to infinity, and the individual orbital angular momentum of the electrons are La and Lb, and the projections of these angular momenta on the z-axis will be MLA and MLB. On the internuclear axis or the z-axis, the resultant projection capital lambda of the molecular state under the condition that R goes to infinity will be written as capital lambda is equal to mod of MLA plus MLB. MLA takes 2L plus 1 values in the range that MLA goes from minus LA to plus LA, including both minus LA and plus LA. And MLB takes 2LB plus 1 values in the range that MLB will change from minus LB to plus LB. The total number of possible molecular states with different values of capital lambda composed of two given atomic states can be quite large. So you see that since there are two L plus 1 allowed values of projections for the MLA, and there are two LB plus 1 allowed values of MLB corresponding to the angular momentum LB, then of course, since there are many values of projections, and you know that delta is actually the sum of those projections. So capital lambda, so capital lambda can have many values possible, and the number of values for this capital lambda could be quite large. So now in the next I am going to take a figure, take an example, so that I can define that how you can construct a different molecular states. A diatomic molecule is formed by the combination of an atomic p state with L is equal to 1 and a d state with L is equal to 2. Find all possible molecular states. A diatomic molecule is formed by the combination of an atomic p state with orbital angular momentum, total orbital angular momentum L is equal to 1, and a d state with the total orbital angular momentum L is equal to 2. Find all the possible molecular states. So you see that this example is being given under the condition that the two nuclei within the molecule will dissociate under the condition of R goes to infinity. And we have atomic p state and atomic d state. The values of LA and LB are given. So this is LA is equal to 1, and this should be LB, not LA. So this LB should also be is equal to 2. So let's compute different molecular states. So since MLA is given, which is equal to 1, so we can have 2LA plus 1, and L is equal to since 1, so we have 2 plus 1 is equal to 3. It means MLA has 3 possible values. It means 3 projections of MLA are possible. And the values of these projections ranging in the range of minus LA to plus LE will be equal to minus 1, 0, and plus 1. And MLB, which is defined by 2LB plus 1, where LB is equal to 2. You know that here, this is not LA, this is actually LB is equal to 2. So putting the value of LB is equal to 2, you have 5 values. So MLB has 5 possible values. So it means that it have 5 number of possible projections on the internuclear distance or the internuclear axis. And these 5 values, according to this equation, will be minus 2, minus 1, 0, plus 1, plus 2. So how many projections will be there? So the values of capital lambda, that is the total number of projections, will be 3 times 5 is equal to 15. So it means that 15 molecular state will be possible. So let's try to write down 15 molecular states. So since capital lambda is equal to mod of MLA plus MLB, so let's construct the maximum value, because the maximum value out of these contributions will be equal to 3. So 3 can be constructed by minus 1, minus 2. Mod of this one will give you mod of minus 3 is equal to 3. And similarly, plus 1 and plus 2, the mod of this one will also plus mod of plus 3 will also equal to 3. So you see that lambda, capital lambda is equal to 3 can be constructed using 2 options. So 2 possible values can be used to construct a value of capital lambda equal to 3. So when capital lambda is equal to 3, then you see that the other combinations will also be combined to give you other values. So the other values of lambda, which we refer to as the intermediate values of capital lambda, as the one we write in atomic physics. Similarly, for the molecular physics, the intermediate values of capital lambda will be equal to 0, 1, 2, and 3, because 3 is the maximum, and out of the above combinations, we can see that 0 will be the minimum, and all the possible values will be 0, 1, 2, and 3. Because here we are considering the mod values of ML plus MB, so all these values will be possible. So the minimum value is 0, the maximum value is 3. All the possible values will be 0, 1, 2, and 3. And the corresponding molecular states will be sigma, capital pi, capital delta, and capital phi. These will be the 4 states that I have discussed over here. So now let's talk about the sigma states are. So you see that these are the states which are possible under the condition that capital sigma was equal to 3. This capital lambda is equal to 3, corresponding to the maximum value. And you know that this maximum value can be constituted when plus 1 will add to plus 2. So I talked about the states when lambda is equal to capital 3. Then how many states were possible in that? 4 states: sigma, pi, delta, and phi. Now let's talk about the sigma state. The sigma state will be possible when lambda is equal to 0. And you know that lambda is equal to 0 will be formed when MLA is equal to 0 and 0, 0 plus 0 is equal to 0. So this is again sigma state. Minus 1 plus 1 will give you 0. This sigma state is referred to as the sigma minus. And plus 1 and minus 1 both will give you again 0. This sigma states will be referred to as sigma plus. So there will be 3 sigma states according to lambda is equal to 0. So you see that when this lambda is equal to 0, this sigma will have 3 states. These 3 states, Now let's talk about capital lambda is equal to 1. That is the pi states. So capital lambda is equal to 1 can be obeyed using these combinations: 0 plus 1, 0 minus 1, because we are considering the mod values, minus 1, 0, plus 1, 0, plus 1, minus 2, minus 1, plus 2. The mod of all these quantities is equal to plus 1. So how many possible combinations there are there? 6. So it means that these are 6 pi states. So with the sigma, we have 3 sigma states, and with the pi, we have 6 pi states. So now let's discuss the number of states with the lambda is equal to 2. So with the lambda is equal to 2, the possible combinations will be 0 plus 2, 0 minus 2, plus 1 plus 1, minus 1 minus 1. And the mod of all these quantities will give you 2 in all these cases. So it means that we have 4 delta states, because when capital lambda is equal to 2, it means that we are talking about the delta states. So how many delta states will be there corresponding to lambda is equal to 2? The delta states will be 4 in the number. So now I am going to talk about capital lambda is equal to 3. That is, I am going to discuss how many 5 states will be there. So 5 states. Since capital lambda is equal to 3, the 3 combination can be obtained using a plus 1 plus 2, minus 1 minus 2. The mod of these quantities will be equal to 3. So it means that 2 5 states are possible. So you see that we have worked out 3 sigma states, 6 pi states, 4 delta states, 2 5 states. How many states are there? 15. So total number of molecular states will be 15 in a number. So the next I am going to discuss electron spins, multiplicity, and fine structure splitting. The coupling of spin angular momenta SA and SB of 2 atomic states A and B is defined by the spin of the molecular state capital S. So capital S has a value that capital S is equal to SA plus SB. The number of possible projections, which are, that the projection of the spin angular momentum are called sigma projections. These are not molecular states. So these are sigma projections. So the number of possible projections sigma of S onto the internuclear axis is determined by multiplicity, which is equal to 2s plus 1. So you see that in the previous pages, I have also shown that how many sigma, how many projections of sigma will be possible. This is according to 2s plus 1. Hydrogen atom in its ground state have spectroscopic notation 1, 2s half. 1 is the principal quantum number, 2 is the multiplicity, half is the value of the total angular momentum of the electron, capital S is the symbol of the state. Similarly, another hydrogen atom have the same state. So hydrogen atom plus hydrogen atom form the ground state H2 molecule. The molecule could be in singlet state with symmetrical spatial wave function with opposite spins, or the triplet state anti-symmetric spatial wave function with parallel spins. And you know that these are the two possibilities for the H2 molecule. Either the H2 molecule has a symmetric spatial wave function with opposite spins, or the triplet state in which we have anti-symmetric spatial wave function, but the spins are parallel. And you know that in the triplet case, the total value of capital S is equal to 1, giving you 2s plus 1 equal to 3. And in the singlet case, the value of total capital S, that is the spin angular momentum quantum number, capital S for the singular state will be equal to 0. Singlet means, so if you put 0 here into 2s plus 1, you will get 2s plus 1 equal to 0. Equal to 1. That's why the state will be referred to as the singlet state. In both cases, the total wave function has to be antisymmetric with respect to exchange of two electrons. So you see that as far as the exchange of two electrons are concerned, we require the wave function to be antisymmetric. Exchange symmetry is labeled S for symmetric and A for antisymmetric. You know that we have been writing S and A for to represent the wave function when it is symmetric, and the wave function when it is antisymmetric. The reflection symmetry is labeled plus with plus sign for symmetric and with the negative sign for antisymmetric. You know that I have also discussed the reflection properties, and we have seen that there could be a positive sign representing symmetric reflection and symmetric wave function, and negative sign representing antisymmetric wave function. The interaction energy W of the electron spin capital S with the molecular magnetic field B, which is produced by the precessing orbital angular momentum. So you know that S and B will interact with each other, and the interaction energy W will be proportional to the scalar product of these quantities. That is, W will be proportional to minus times the scalar product of S and B. B is proportional to the projection lambda times h bar, because B is produced by the angular momentum quantum number, angular momentum, orbital angular momentum. Since B is produced by that one, so B is also, that's why B is proportional to lambda times h bar. And the spin projection mod of ms, you know that we already designating the mod of ms by the symbol capital sigma. So the spin orbit interaction can be written as A times capital lambda times capital sigma. You know that you can expand this quantity is S dot B. So S dot B could be equal to S magnitude, B magnitude, and the angle between them. Or you can write that angle with, if you write that angle with S, you can write it as sigma. If you write that angle with B, you can write capital lambda. So in order to accommodate both of these one, I have used a constant of proportionality A. in order to write that proportionality shown in equation number 105 in terms of the equation shown in equation number 106. A depends on specific molecular state called molecular fine structure constant. A depends on the specific molecular state called molecular fine structure constant. So you see that A is the molecular fine structure constant. A molecular state composed of atomic states with angular momenta L, A, L, B with sigma with capital lambda not equal to 0, capital S not equal to 0 will split into two S plus 1 fine structure components. So you see that here I have mentioned that if capital lambda is not equal to 0 and capital S is not equal to 0, then a molecular state composed of atomic states with an angular momenta LA and LB will split into two S plus 1 fine structure components. The complete labeling of a fine structure constant component is complete labeling of a fine structure component is. So you see that the molecular state is given by lambda, capital lambda. The multiplicity is given by 2s plus 1, written as a super superscript, and as a subscript we have written the value of capital omega, which is the total projection. So you see that since capital omega is equal to capital lambda plus sigma, because capital lambda is the projection associated with the angular momentum and capital sigma is the projection associated with the spin angular momentum. So this lambda, we have seen already that this is equal to mod of projection of ML, which is MLA, and the projection of MLB, which is MLB over here. So the mod of MLA plus MLB, and you know that these MLA, ML has values of minus L to plus L, both MLB and MLA. And this sigma has these values, that sigma can have values from minus capital S to plus capital S. Now let me discuss a simple example so that I can elaborate this fine structure splitting further. A diatomic molecule is in an electronic state with capital L is equal to 2, capital S is equal to 1. Show the fine structure splitting. So a diatomic molecule is in an electronic state with capital L is equal to 2 and capital S is equal to 1. Show the fine structure splitting. Capital L is equal to 2 is composed of capital LA and capital LB. The possible combinations are LA and LB to form capital L equal to 2 will be 0, 2, 1, 1 and 2, 0. So then you can construct a capital L is equal to 2 over here. Let us choose LA. You know that many values of LA and LB are possible. So 3 values of LA and 3 values of LB are possible. So let's choose LA is equal to 1 and LB is equal to 1. So I have chosen the middle set. LA is equal to 1 and LB is equal to 1. MLA will have following projection values minus 1, 0, plus 1. Similarly, MLB has values minus 1, 0 and plus 1. And capital lambda is equal to mod of MLA plus MLB gives many values. You know that I have used only positive values with LA and LB to produce capital L is equal to 2. L is equal to 2. Negative values are also possible. So you see that this lambda, capital lambda, defined by the mod of MLA plus MLB can give you many values. So let's choose only capital lambda is equal to 2 only. So out of many possible values, I am choosing capital lambda is equal to 2 only. So when capital lambda is equal to 2, it means that I am talking about the delta state. The molecular state will be delta when you choose lambda is equal to 2. And this corresponds to lambda is equal to 2 only. Now you see that when capital S is equal to 1, this sigma, which is the projection of projection values, have these projection values. The sigma is equal to -1, 0, +1. So omega, which is the total projection, is equal to the sum of our projections due to capital lambda and capital sigma. You know that we have fixed its value. Capital sigma is equal to 2 always. We have fixed its value in this example. So lambda is equal to 2 and sigma has a value of given in the set -1, 0, +1. And of course, the total value of omega will be equal to 1, 2, 3. Now the fine structure terms will be 2s plus 1. The state is sigma. Sorry, the state is delta. So this capital lambda, since corresponds to 2 and the molecular state will be delta. So I have used delta over here because capital lambda is equal to 2 will give you a state equal to delta. I have used the value of omega as a subscript as 1, 2, 3, and the multiplicity, which is equal to 2, s plus 1 is equal to 3, because capital S is equal to 1. So the the distribution in the order of increasing energy of the molecular state is 3 delta 1, then higher state is 3 delta 2, then further higher electronic state is 3 delta 3. The energy separation of these states is given by, as we have seen earlier, so W is equal to A into capital lambda into capital sigma. This will give you the separation between the states. For the 3 states, capital lambda is equal to 2 and omega is equal to 1 to 3. And if you get the value of sigma from the previous equation, so sigma will be equal to omega minus delta. Since omega is equal to 1 to 3, delta is equal to 2, so sigma is equal to -1, 0, and 1. And we have already written the value of sigma already. If you notice over here, you don't need to use this equation because sigma is already -1, 0, and +1, and capital delta is equal to 2. Capital lambda is equal to 2. So 3 delta 1, since I am using a state delta, which means capital lambda is equal to 2, and this subscript indicates that lambda is equal to, because you see that for this state lambda sigma was -1. So the energy, this W, putting the value of capital lambda and capital sigma, you will get that is equal to -2A. Similarly, for 3 delta 2, capital lambda is equal to 2, sigma is equal to 0. So putting this value, you will get W is equal to 0. So for 3 delta 3, capital lambda is equal to 2, sigma is equal to +1, and the W will be equal to 2 times +2 times A. You know that these are the values of sigma which was used in order to constitute the state of the molecule. For example, when you use -1, you will get a delta is equal to 1. When you use 0, you will get a delta is equal to 2. When you use +1, you will get a delta is equal to 3. So 1, 2, 3 means that -1, 0, and +1. So the term values of these fine structure constants are this is defined by this term value as a function of capital lambda and capital sigma is equal to T naught plus W, and W was equal to A times capital lambda times capital sigma. This is the term value of these structure constants, of these structure components for the value. And you know that we were discussing a case of a capital L is equal to 2, capital S is equal to 1. And you know that I have taken only out of many possible values, I took capital lambda is equal to 2. And then you see that over sigma was is equal to plus 1, 0 and minus 1. So according to these, there will be three states: 3 delta 3, 3 delta 2, 3 delta 1. The lowest in energy is 3 delta 1. The middle in energy is 3 delta 2. The top one in energy is 3 delta 3. The separation between each of these is 2a, which you can see from here. From the center one, the lower one is at 2a. From the top one, the lower one is at 2a. So the separation magnitude is 2a of each fine structure splitting. So let me read the caption. Fine structure splitting of a molecular state with lambda is equal to 2 and sigma is equal to 1 into 2s plus 1 delta omega equidistant components. The fine structure components are equidistant and are separated by a times capital lambda capital sigma. And you know that here I have discussed the case when lambda is greater than sigma. So lambda was 2, sigma was equal to minus 1, 0 and plus 1. But you know that if we discuss the case in which omega is less than sigma, then of course there will be some components in which the positive sign quantities and the negative sign quantities will also be present. So the components, fine structure components that differ only in sign of omega, that is the quantities with the plus omega sign and minus omega sign, will then be possible under the condition that capital lambda is less than capital sigma. Then such levels will be degenerate levels. That is the levels with the positive values and with negative values will be degenerate in the non-rotating molecule. But when the molecule will rotate, the degeneracy will be lifted, which we are not discussing in the present lecture. So you see that I have discussed the fine structure in its simplest form, discussing simplest cases out of many possibilities for the molecular states. I have discussed the simplest states or the chosen states. So this is the end of lecture 18D. So you see that this is the fourth lecture of the molecular states of diatomic molecules. The lecture is continued, and there will be probably, for example, maybe many lectures concerning dealing with diatomic molecules. So please wait for the next lecture.